This is problem set number 6, problem 6. Consider a two-layered spherical ball of total radius 2r. The inner core of the ball has radius r and charge density rho 1. The mantle, or the outer shell, extending from r to 2r, has charge density rho 2. Points A, B, and C are labeled for later reference. Charge density is in charge per volume. Part A, what is the total charge of this ball? Okay, so we have a two-layered spherical ball, right? And you can see that the first layer is this inner shell here with charge density rho 1 and radius r. And the second layer is this outer layer here with a darker shade. And it has charge density rho 2 and a radius of 2r. Okay. Part A, what is the total charge of the ball? So, oops. Part A, total charge of ball. Okay. So in order to answer that, I'm gonna use the fact that rho, or charge density, I'll just keep it simple. So charge density is equal to charge divided by volume, or charge per volume. That is equal to charge density. Okay, so this is charge density. This is charge per volume. Okay. So another formula that I'm going to use is the formula for the volume of a sphere. So the volume of a sphere is equal to 4/3 pi times the radius cubed. Okay. And these formulas are, you should either know by heart or have in your formula sheet. And that should help you during a test. Okay, so I want to know the total charge of the ball. So using this formula for charge density, I could figure out charge, right? So basically, if the total charge density is equal to the total charge of the ball divided by the total volume, then I can say that the total charge is equal to charge density times total charge density, which actually density doesn't change, or it actually does in this case, doesn't it? So total charge density times total volume. Okay, so in this case we'll have to split that up since we have different charge densities and different volumes for the inner layer as well as the outer layer, right? Okay, so this becomes that's equal to density 1 for the inner layer times volume 1, right? Plus charge density 2 times volume 2 for the outer layer, right? So this guy right here corresponds to the charge density and volume for this inner layer. And this guy right here corresponds to the charge density and volume for this outer layer, okay? So let's break that down. Well, first let's break down what's V1 and V2. Okay, so V1 is the volume of the inner layer. So volume of inner layer, okay, that's V1 is equal to, we've got this formula right here, right, for the volume of a sphere. So that is equal to, actually, I'm sorry, I'm gonna use a different color there, just so it's clear that that's kind of a side quest. So volume of inner layer, V1 is equal to 4/3 pi. And what is the radius for the inner layer? It's capital R, right? That's seen in our diagram. So R cubed, okay? That is our volume for the inner layer, which we'll call V1. All right? So volume of outer layer, we'll call that V2. What is that equal to? As we can see here, our outer layer extends from R to R2, right? Right here. It goes right here from 2R to R, right? That's our outer layer. So in that case, that will be, 4/3. Hold on. I'm going to make this a little smaller. Move it down. All right. So that's going to be 4/3 pi of, my radius here now is 2R, right? So I'm going to cube that. And I'm going to subtract that by this volume. So that would be 4/3 pi R cubed, right? So basically that was this, I was just subtracting this inner layer from this total outer layer, okay? So that is the volume of my outer layer. Okay? I'm gonna make that even smaller. Okay. So now I'll plug that in to my formula right here. So that's gonna be rho 1 times my V1, which is 4 pi R cubed divided by 3, right? Plus rho 2 times V2, which is this guy right here. So rho 2, that would be 4 pi 8R cubed rho 2 divided by 3 minus 4 pi r cubed rho 2 divided by 3. Yep. So this is our P1V1, and this is P2V2. Okay. So let me see. I could do better than that. So that would be 4 rho 1 pi r cubed over 3 plus 4 times 8, that's 32 rho 2 pi r cubed divided by 3. And that's minus 4 rho 2 pi r cubed divided by 3. Okay. I have like terms, right? I could put these two guys as one fraction. So that becomes 4 rho 1 pi r cubed divided by 3 plus 32 minus 4, that's 28 rho 2 pi r cubed, divided by 3. Okay, so my answer for part A is my total charge is equal to, I'm going to factor some stuff out, like 4 pi r cubed divided by 3. So rho 1 plus 7 rho 2. Okay, so that is my total charge of my ball. This is my final answer for part A. Okay. So let's go to part B. What is the electric field at point A, which is a distance of RA from the center of the ball? As the diagram indicates, RA is greater than 2R. Okay, let's add that photo in here. So what is the electric field at this point A, which is a distance of, we're calling this RA, okay, radius A, from the center of the ball. And so to do that, I'm going to use the formula for electric flux, which is electric flux is equal to, actually I'll write that in blue because I like to write my formulas that I think you guys should have in your cheat sheet in blue. So electric flux is equal to the surface area integral of electric field times dA, which is also equal to charge enclosed divided by epsilon naught, which is a constant. Okay. So I'm basically going to use this formula to solve for the electric field at point A. As far as my Gaussian surface, I'm gonna create a, I'm gonna create a sphere with radius RA, all right? So this is my Gaussian surface. And let's try to figure this out. Oh, also another thing to know, surface area for a sphere is equal to 4 pi r squared. Don't know if I mentioned this, but all these formulas I have in blue that's boxed, I do that so that you could hopefully have that in your formula sheet or your cheat sheet for the test. So this is the electric flux. Okay. This is the electric field right here. And this is the Gaussian surface area, or it will be after you take the integral. And this is the charge enclosed in my Gaussian surface area, or in my Gaussian surface, okay? This is just a permittivity of free space, that's a constant, okay? Alrighty. So let's get back to the problem. So my Gaussian surface is a sphere, so that means that the vector normal on my surface is going to be parallel to the electric field coming from this ball, right? So then what that means is the E here will just be a constant, so I'm going to take that out. So E times surface integral of dA from my Gaussian surface equal to charge enclosed divided by epsilon naught. Okay. My Gaussian surface area is a sphere, so I'm going to use the surface area for a sphere right there, that formula, 4 pi r squared. So that becomes E times 4 pi, and what is my radius for my Gaussian surface area, which is this guy. What is the radius for my Gaussian surface area that I'm using now? It's RA, right? So then that would be RA squared. That's going to be equal to the charge enclosed, which, what is the total charge enclosed for this ball? We don't need to solve for it because we solved for it in part A. The total charge enclosed is this. I'm just going to copy that down for charge enclosed. 4 pi r cubed over 3 times, I'll just use parentheses, times row 1 plus 7 row 2. Okay, and I won't forget this epsilon naught on the denominator, so I'm just going to put that down here. And then I'm going to transfer this Gaussian surface area for the sphere to the right side of the equation, and I can find my electric flux at point A. So that becomes my electric flux at point A is equal to, I'll call that electric flux at point A, is equal to 4 pi r cubed over 3 epsilon naught times times rho 1 plus 7 rho 2. And when I move this equation to the, or this term to the right side of the equation, I'm going to divide it by 4 pi RA squared. All right, I'm going to cancel out some terms. So 4's cancel out, pi cancels out. I think that's it. So my electric field at point A, which is the distance RA from the center of the ball, is equal to R cubed times rho 1 plus 7 rho 2 divided by 3 epsilon naught RA squared. Okay. So that is my final answer for part B. Okay. So part C. What is the electric field at point B, a distance of RB from the center of the ball? Since B is the mantle, RB is going to be between length R and 2R. Okay. So let's look at what that looks like. So point B that we want is right here. We want to find the electric field at point B, right? And they said that this is a distance of RB from the center of the ball. And they also said that RB is going to be between this distance R and 2R, which we can see is true, right? Because it's somewhere right here. So it's between R and 2R. All right, that's fine. So let's get on it. I'm gonna use the same formula I did earlier, which is the electric flux formula. I'm not gonna write it in blue this time since I already wrote it in blue here, and hopefully you guys will have that in your cheat sheet. All right, so electric flux is equal to the surface integral of the electric field times dA, which is equal to the charge enclosed divided by the constant epsilon naught. Okay. So I'm gonna put a Gaussian surface right here, also a sphere, right? And my Gaussian surface is going to have a radius of, I already wrote it down, of RB right there. Okay, that's going to be my Gaussian surface's radius. All right, so this is going to be, the E is going to be constant, so I'm going to take it out, right? For the same reason as I mentioned in part B. That's going to be E times the surface integral of dA, which is equal to charge enclosed divided by epsilon naught. Okay, what is my Gaussian surface area? So that's going to be the surface area of a sphere, which is 4 over 3 pi r cubed. So that's going to be E times 4 pi my radius for my Gaussian surface, right, is RB. So that's going to be RB cubed. I'm sorry, did I say cubed? That's for volume. The surface area is 4 pi r squared, so that should just be 4 pi rb squared. Okay. So that is equal to my charge enclosed divided by epsilon naught. Right? But what is my charge enclosed? What is the charge enclosed here? Well, let's solve for that. I'll use brown, which is our usual side quest color. So side quest, let's look for Q enclosed, right? So as we said earlier, surface charge is equal to charge divided by volume. Okay, so the charge is equal to charge density times the volume. Okay, so charge density enclosed is going to be equal to this guy, the charge density of the inner sphere times the volume of the inner sphere, plus this guy, which is this guy right here, right? And that guy is going to be the charge density 2, because it says it right here, right? This part has a charge density of 2 for all this darker shaded region, the outer layer. All right, but this time the volume is going to be the volume, which is going to be volume of our Gaussian surface minus the volume of V1, all right? And the reason for that, if it was not clear, is because we have, for this guy, we have only charge density 2 is only for this volume, which is the volume of the Gaussian surface right here, that outer layer, right? The outer layer right here. Oops. Right here. Minus this guy, because this is not included, right? We only go here. So that's volume of the Gaussian surface minus V1. Okay. All right. I'm going to make this a little bit smaller. So that is equal to rho 1. And what is V1? That's volume of a sphere is, so V sphere is 4 over 3 pi r cubed, okay? If you guys didn't know. So 4 over 3 pi, what is the radius of the inner sphere, which is V1? It's just r, right? So r cubed plus rho 2 times the volume of our Gaussian surface, which is 4 over 3 pi rb cubed, okay, minus V1 again, which is 4 over 3 pi r cubed. Okay? All right, so that becomes 4 pi r cubed rho 1 over 3 plus 4 pi rb cubed rho 2 over 3 minus 4 pi r cubed rho 2 over 3. All right, and I'm gonna group these terms together since I could factor out 4 pi r cubed over 3. So that becomes 4 pi r cubed over 3 times rho 1 minus rho 2 plus 4 pi rb cubed rho 2 over 3. And that is my charge enclosed, okay? Put a cloud over it. Okay, so I'll just plug that cloud in for Q enclosed here. So that's 4 pi r cubed times rho 1 minus rho 2 plus 4 pi rb cubed rho 2 divided by 3 epsilon naught. Okay. I'm going to make this a little smaller because don't have enough space. Okay, so I'm just going to move this term for the Gaussian surface area to the right side of the equation so that I could find my electric field at point B. So E is going to equal 4 pi, I'm not going to rewrite that because that would be ridiculous. Copy. That's beautiful. Okay, so I'm going to divide it also by 4 pi rb squared. Okay, so cancel out like terms, so 4 cancels out, pi cancels out, and I could also cancel out rb for the right side numerator term, which I will do. Okay, so electric field at point B is going to be equal to r cubed times rho 1 minus rho 2 divided by 3 epsilon naught rb squared plus, on the right term, I could cancel out the rb squared in the denominator with rb cubed on the numerator. So then I would just be left with rb rho 2 divided by 3 epsilon naught. Okay. And that's going to be my final answer for my electric field at point B. Okay. So now moving on to part D. Part D, what is the electric field at point C? A distance RC from the center of the ball. C is in the core, so RC is going to be less than R. Okay. So let's again take a moment to see what that looks like. Okay. So for part D, I want to find what is the electric field at point C, right here. And they said that that is a distance that they're calling RC from the center of the ball. So this is a distance RC. Okay? So same as part A, B, and C, I'm going to use the electric flux formula. Right? So that's going to be equal to the surface integral of the electric field times dA naught. Okay. And because the Gaussian surface that I am choosing will be a sphere right here with a radius RC. I know my circle isn't perfect, but imagine that's a perfect circle in pink. Okay, so that's my sphere, my Gaussian sphere, my Gaussian surface. It's a sphere. So obviously it's a sphere, so the vector normal for my Gaussian surface is parallel with the electric field that radiates out from this this inner layer with a charge density ρ1. So my electric field is a constant. So I'm going to take that outside. I'll get the surface integral of dA is equal to Q enclosed divided by epsilon naught. Okay. So that becomes E times my Gaussian surface area, which is going to be the surface area of a sphere, which is 4 pi r squared. So 4 pi r squared. But what is my radius? My radius of my Gaussian surface is this RC, right? It's that radius of this pink sphere, RC. So that's going to be RC squared is equal to Q enclosed over epsilon naught. What is my Q enclosed? We'll have to solve for that real quick. So Q enclosed will be equal to, what is the charge density here? Actually, it's the charge density in this entire inner surface. That's going to be ρ1. That's a charge density. And what is the volume that I'm going to use? I'm going to use, in this case, the volume of, the volume of my Gaussian surface right here. Okay? That's going to be for the charge enclosed. So everything enclosed in this surface. My Gaussian surface, that's going to be 4 divided by 3 pi r c cubed. Okay? So I'm going to put a cloud around that. And I'm going to plug it in to my Q enclosed, my charge enclosed. That's going to be 4 pi ρ1 RC cubed 3. And then don't forget this epsilon naught in the denominator. I have a habit of forgetting that, but this time I didn't, so there you go. And so now we have everything we need to find the electric field at point C. So let's go ahead and do that. So I'm going to bring this term to the left side of the equation by dividing it from both sides. So I'll be 4 pi rho 1 RC cubed divided by 3 epsilon naught times 4 pi RC squared. Okay? So now let's cancel out like terms in numerator and denominator. 4 pi RC squared will cancel with a cube. So we are left with electric field is equal to rho 1 RC divided by 3 epsilon naught. And that'll be our final answer for part D. That is the electric field at point C. Okay, hope that was fairly clear.